The next thing that I'd like to talk about is the deuteron. And deuterium NMR is one of the most useful techniques in studying the properties of biological membranes. And Dr. Kepi's group in our department has really done a lot of work on that. It turns out that I did my PhD thesis on deuterium NMR and also another topic I'll get into a little later, way back nearly 50 years ago now. And I determined some of the important parameters that are still in use today for using deuterium NMR to study biological membranes. So let's flip back to deuterium NMR then. And and I'm going to give the example of just a methyl group. So let's first talk about a methyl group here that's sitting like this. And one of these is going to be a deuteron. I'll use the D, but the other symbol would be, it's a hydrogen atom with a atomic weight of 2. You know, a deuteron is a proton and a neutron together. And so we've got this deuteron sitting there. And the thing about the deuteron is it has a spin is equal to 1. The spin of the proton, as I've indicated over here, is 1/2. And that means that the spin along the magnetic field can assume the values of -1, 0, and +1. And that's true for any nuclear spin. Depending on what the value of the I is, it changes by integer values between the minus the number of I all the way to plus the number of I. We'll just be talking about spin 1/2 and spin 1 nuclei in this class, but there's other nuclei that have larger spins than 1 and it gets more complicated. So let me draw a little diagram here. And the thing that's important about the deuteron is because it has a spin of 1, it has something like a quadrupole moment. And what that means, it's not shaped like a sphere. The nucleus of the deuteron is not spherically shaped, but it's shaped like an ellipsoid, okay, kind of egg-shaped. And I'm going to expand the size. Obviously, the deuteron is very tiny compared to this, but I'm going to expand it. And so this is going to be the state with +1. And this here represents that very tiny localized positive charge of the carbon nucleus. It's surrounded by the electrons, but they're much more diffuse. So that is the carbon nucleus. I'll just put that right in there. So that's what I mean there. And that is a very intense positive charge, okay? The charge of the carbon atom. And then the deuteron has a nucleus with this egg-shaped. And this is going to be the spin state here with the spin going up like this, okay? And so this is going to be +1 is equal to Mi. And then when the deuteron is facing this way, it's going to be egg-shaped that way. And that would be M sub I is equal to 0. And here's that same thing there. And then the third state is going to be this state here with M sub I is equal to -1. Okay? And here's that here. So we have this same type of energy here because of the interaction of the magnetic field with the magnetic moment, but we have this additional quadrupolar coupling here. And which of these do you think is going to be the highest in energy? Remember, the charge on the deuteron is positive, the charge on the carbon nucleus is positive, we have the diffuse cloud of electrons that's partly shielding that positive charge from the deuteron, but since that's highly localized and this is diffused, it doesn't completely shield it. So which is going to be the lowest in energy here, or the highest in energy? You see here, this gets that part closer to that positive charge that's unfavorable, so that will increase the energy. That shape gets it further away, so that's going to be lower in energy. And this shape is the same as that one as far as the quadrupolar interaction is concerned. So I'm going to draw another little energy diagram here. And so this is going to be no magnetic field. And then I'm going to add in just the effect of the spin itself before we add in the quadrupolar effect. And that's going to separate it into these three states here, which is going to be -1, 0, and +1. And we can get a transition between the -1 and the 0, or the 0 and the +1, and the energies are the same. So that would give rise to a single NMR peak, okay? Now I'm going to add in this quadrupolar effect here, and as I've indicated here, what that's going to do, these two states will rise in energy because it's bringing that positive charge in the nucleus closer to the carbon nucleus. So that's going to go up like that. This one gets it further away, so that's going to go down like this. And this one is going to go up like that. Now I'm exaggerating this a bit, but that's going to split this transition into a lower energy transition, and that transition into a higher energy transition, okay? And so what that would do is that if we had, without the quadrupole interaction, we would have a single peak in the NMR spectrum. We would get a doublet that is right halfway centered on the original single peak. This splitting here is called the delta mu d. That's the quadrupolar splitting of the deuteron, okay? Now, I need to do one more thing here to really show you how this all works. Let me erase this stuff. Put something different down here. So what I'm going to do now is I'm going to rotate this molecule by, we'll just try it by 90 degrees here. So I'm going to put the carbon here, the deuteron here, and the methyl group out here. And I'm going to put here, the carbon nucleus will be here. This same state with Mi is equal to +1 is going to look like this. This state here is going to look like this, okay? And this state here is going to look like this. Again, this is +1, 0, and -1. Now, which do you think is going to be lowest in energy here? This state or that state? And again, this gets that part of it closer to the carbon, and this one gets it further away. So that's going to be lower in energy, that's going to be higher in energy. And what I'm going to do is I'm going to superimpose this different splitting for this different orientation on that same diagram, hopefully using a different colored ink. I don't have a red, but I'll hopefully use blue. So this +1 state is going to lower the energy. So it's going to look like this. The 0 state here, that's going to be the highest energy. That's going to look like this. This one here is lower in energy. So this time, as we go from here to here, that will be higher in energy, this will be lower in energy. So what's going to happen here is we go from these different orientations is we are also going to get a doublet here, but it is going to be flipped, and I'll just draw it as a different value here. We'll get to the numbers later. But this line is going to go over here. This line is going to go over here. So they come together and then they flip. Okay? Now I'll show you the equation for that a little bit later. The net result of this is if we have, say, a methane molecule with one deuteron in aqueous solution, it's undergoing all possible rotations, right? That would all average out, and we'd end up with this line here. Because some of the molecules would be like this, some would be like that, some would be like this and flipped, and the average of all these would be just a single line. So if you have a liquid solution in which you have all the possible motions, you just wouldn't see this at all. But if you put this deuteron in a membrane and you don't have all possible motions, then the appearance of this, the splitting, would tell you what type of motion you have. Okay? That's why this is so powerful. And you can put a deuteron any place in the membrane you want, on any one of the carbons on the hydrocarbon tail, and use that to determine the motion. And that's what Dr. Kepi's group does quite a bit. And now let me bring in the actual equations so you can see how this thing works. So let's bring this over here. Has everybody got everything this far? I'll leave that on the board, but I'll